Hello everyone. So I just remind you that we are in this paragraph 2.4 about the general Pfaffian formula. And what did we do so far in this paragraph? So we had fixed a graph G in a surface, and we had devised a rule to associate to a given perfect matching. So if we fix a perfect matching on the graph, and if we also fix an orientation on the graph, then with all of this, we had devised a way to construct a vector field. So I had given a rule. So basically, well, the result here was going something like that. So this is a vector field, which I can denote this way. And the first result that I had was basically saying, so then, I was extending it to the faces, and the first result I had was basically saying that, so this vector field has zeros, only zeros of even index, if and only if omega is a Castellan orientation. Okay, and then the question was, does there exist always a Castellan orientation? And that was a proposition, which I was in the middle of proving. So there exists such an orientation. If and only if the number of vertices of the graph is even. In this case, then, the set of equivalence classes of Castellan orientation, remember equivalence class means, well, two orientations are equivalent if they are related by switching orientation around vertices. Then the set of equivalence classes of Castellan orientations is an affine space over this space. In particular, it means that it's in bijection with this space. So in particular, the number of equivalence classes of Castellan orientations is 2 to the power 2g, where g is the genus of the surface. If you're in the plane, there is essentially a single Castellan orientation. If you're on torus, there are 4, etc. So I had already proven the first part. So as for the second part, let me just give you the start, and the details are going to be in an exercise. So let C1 denote, so we had already introduced this notation, but you can just see this as the maps from the edges of G to Z2. And let's denote by O all the orientations on the graph. So consider the map, consider the action well, the map. So we want to see this as an action of C1 on a set of orientations given how. So phi omega goes to some notation for this action where so how can such a map act on the set of orientations? There is really one sensible way to do so, is that you have a fixed orientation and you want to know how this thing acts on this orientation on the given edge. Well, this will be equal to omega of E if phi of E is equal to 0, and it's going to be different if phi of E is equal to 1. You understand this map? So you just say you have an orientation, you have a map on edges, and the way this map on edges acts on orientation is saying you switch the orientation whenever this map has value 1 on the corresponding edge. Okay, that's just what it means. And then you just check well, the first thing you check is that if, so I don't know if you remember, this was we had some kind of sequence with C1, C2, etc. And we had these kind of boundary operators. And if this operator we had acting on phi is equal to 0 and omega is Castelline, then the result of this action is still Castelline. Hence, this induces a map or an action from the kernel of this operator on the set of Castelline orientations and then you just have to check that that it gives a well-defined map. So here, if you have this kernel, then you have to mod out by the image to get the H upper 1, and you just check that it induces a map from H upper 1 on the equivalence classes of Castelline orientations which defines a freely transitive action. Again, these, of course, it's just many words, but you just have to unwind the definitions, and it's completely immediate. So this is a homework. So exercise 1, homework 7. The point for us is, the main point, I guess, is this, is that actually you have essentially 4 to the power j different Castelline orientations on the graph embedded in the surface of genus G. Okay, I'm just going to leave this drawing here because we're going to need it. But let me just summarize where we stand now. So summary. So we have this construction I just described up here gives you what? So for any fixed perfect matching, we have a map. We have a map which goes from the set of Castelline orientations on the graph embedded in the surface to the set of vector fields on the surface with zeros of even index. And so I had denoted this as above. To omega, I associate x omega m. But now remember that there is a recipe, it's Johnson's theorem, which whenever you have such a vector field, it associates directly a quadratic form on H1 of the surface. That was Johnson's theorem. So here you go to the set of quadratic forms. I think I had introduced this notation, meaning quadratic forms on H1 of the surface with respect to the intersection form. So it means whenever you have a vector field, in particular this one, you can associate a quadratic form. So let me write it this way. So if I summarize, whenever I have a Castellan orientation, whenever I have a fixed perfect matching, and whenever I have a fixed Castellan orientation, I have a map here which is a quadratic form. We know for free it's a quadratic form. We don't have to prove anything for this. But all of this is completely explicit. This first part here is completely explicit. It's what I just described here, summarized here. And this part here, we had this statement of Johnson's theorem. It's completely explicit as well. So actually, I have a map like this, which is completely explicit. So now since it's explicit, I can actually give a precise description of this map here. So that's the next proposition. The quadratic form Q omega m, so it's defined on H1 value in Z2, is characterized by the following property. If C is an oriented simple closed curve on the surface, on the graph, sorry, is an oriented simple closed curve on the graph surface, then what is the value of this form on the class, on the homology class of this curve? Well, it's very simple. It's n omega of C. Remember, C is oriented. It makes sense to count the number of times the orientation on C does not coincide with the orientation omega, plus something which I will explicit in 1 second, Lm of C plus 1 modulo 2. Where, so I continue here. So I need to tell you what this Lm of C is. So it's the number of vertices on the curve where, so I'm just going to be a little bit sketchy here. So it's a precise definition. I'm just not writing it in full English words. So you look at the vertex which is on the oriented curve here, and I'm counting the number of vertices where the adjacent dimer of M sticks out to the left, hence the name Lm. You see, so you have your oriented curve, you're on the surface, you have a fixed vertex, and you have a unique dimer sticking out from this vertex. It can be on the curve, then it doesn't count. It can be to the right, it doesn't count. It can stick to the left. In this case, we counted. Okay. So that's the explicit form of the quadratic form, and I'm going to just state one more fact. Furthermore, the map which to a given Castellan orientation associates this quadratic form induces an H1 Z2 equivariant bijection from the set of equivalence classes of Castellan orientations to the set of quadratic forms. We know since 2 weeks or so, maybe 1 week, that this set has a freely transitive action of H1. We just proved without details that this set admits a free transitive action of H1. And now I'm saying that this map here actually is compatible with this action. So it's a bijection which is natural with respect to the action that we have. So let me pause now and explain why this is a remarkable statement, this proposition. And then I'm going to prove it. So actually this statement has a huge combinatorial content that we don't see immediately. To explain to you why it's a very strong combinatorial statement, let me just give you an example. And it's going to remind you of something, I hope. Example, let's just take the case of the plane, g equals 0, the plane. In the case of the plane, this h1 here is 0. So it means this number here, so quadratic forms on 0 must be 0 all the time. So it means that this thing here must always be 0. So it means that this thing here must always be odd. So the statement we have in the planar case is saying, well, you take any Castellan orientation, you take any perfect matching, you take any simple closed curve, this number is going to be odd. And you see it resembles, it's basically the same thing as one of the lemmas we had in Castellan theorem. Remember? We were saying you're enclosing, well, it's exactly lemma B of Castellan theorem. So in this case, it says, for any perfect matching, for any Castellan orientation, for any oriented simple closed curve C, we have that n omega of C plus L m of C is odd. So I am not claiming that this is a very, very difficult theorem. You can indeed, in the plane, you can prove it the way we proved it in Castellan theorem. You make an induction on number of faces that you enclose, and it works. Okay. So this is just, but you see, we have this for free. We didn't do any combinatorics. But then, if you want to try to extend this kind of statement to any curve on any surface, you see the kind of trouble you run into. It's just extremely complicated. And now we have it completely for free. We have that this thing here, this number here, only depends on the homology of this cycle, for example. You see, in the plane it's completely trivial, but already in the torus, it's not trivial at all. Okay. And we have it completely for free. We didn't do any combinatorics. We just used the power of geometry. Well, so we actually translated everything into a theory where you have more flexibility, that is geometry, basically. And in geometry, you can prove this theorem of Johnson. It's not a difficult theorem. I didn't prove it, but it's not difficult. And then you just translate back everything into combinatorics, and you have this statement here, okay, completely for free. So, okay, I'm going to prove this, this statement. It's very easy. And then I'm going to show you how it allows us to prove the full Pfaffian formula. So, proof. And okay, so we have to remember how it was defined in how it worked for Johnson theory. So let C be a closed-oriented curve in G. So by Johnson's theorem, the very definition of Q omega m of C, it was really defined as, so I had denoted it this way. It was winding of the curve with respect to the vector field. So here it's many indices plus 1. It was just, if you just look at the statement of Johnson's theorem, that was what we had. Where this means what? It's the winding number of the velocity vector field of C with respect to x. So winding number of velocity vector field of C with respect to x, so in this case x omega m. So if we want to see that these two numbers are the same, we just need to check. So we need to check that this winding number has the same parity as n omega of C plus L m of C. This is what we need to check. Okay, I have to erase this. And this is very easy. You just, so the first thing you check is that if you invert omega on, so if you invert omega on one edge, then both of these things will change. The parity of both of these will change. So it's, of course, true for this number here. And for this, you have to check. But it works. So first note, so note that both sides change parity, so change if we invert omega along one edge of C. So we can assume that n omega of C is equal to 0. Well, actually, we can assume that, yeah, that's right. So omega is exactly, always goes in the same direction as C. And also, both sides change if we replace So I'm just going to write it this way. So if we replace a dimer sticking out to the left by a dimer that does not stick out to the left, so it means it can stick out to the right or be on the curve itself. So we can assume that Lm of C is equal to 0. And then, and this is the reason why I kept this drawing here, in this case, you find yourself with no dimer sticking to the left, and you find yourself with the omega always being in the direction of C. Then in this case, you see that the vector field is homotopic to a vector field that always points outside, well, always points to the right. So in this case, x omega m is homotopic to, so I'm going to draw a curve in the plane, but of course it's on the surface in general, so it's going to be a curve that, so it's homotopic to a vector field that always points to the right. And in this case, what is the winding number? Well, you see that the velocity vector field is then constant with respect to this vector, so the winding number is 0. So this works. And so I just need to prove this last part. I will not give all the details, but this is easy now. So this map induces an H1 equivariant bijection. So the first thing we have to check, so now since we now have this equality, so n omega c, if omega and omega prime are equivalent, then q omega is equal to q omega prime. You see? So if you take a vertex and you change the orientation around, on all the edges adjacent to this vertex, when you have a simple closed curve like this, it will change this thing by 2, so the parity does not change. So it means that indeed we have a map from this set to this set. So we do have a map from the set of equivalence classes of Castellan orientations to set of quadratic forms. And finally, by the equality above, again, we have, so if you look at Q associated to, remember we had this action of phi on the orientation omega, M, this will be equal to Q omega M plus phi. You just look at the definitions and it works. So this means, so then it means that this map is equivariant, and then since these two are affine spaces, then it's automatically a bijection. This implies the last statement. So there is something I had forgotten to say, I should have said at the end of the last proposition. So a first remark, and then I'm going to state a corollary of this, this proposition we just proved. But a remark I should have said before, a late remark, is, so we just said that there is, so the last proposition, there are 4 to the power g different Castellan orientations. Question is, how do you get, if you have one Castellan orientation, how do you get the other ones, the non-equivalent ones? So, given a Castellan orientation on a graph in a surface, the way to obtain the non-equivalent ones is as follows. You pick a cycle in sigma which represents a homology class that is non-trivial, non-trivial class in the homology, and you want your cycle to be transverse to G, and then, so let's say gamma, the cycle, and you change omega whenever gamma intersects an edge. You see what I mean? So let's say, for example, that you're on a torus. And let's say that, okay, you have your graph. I'm not going to draw the graph. And you have a fixed Castellan orientation. The way you're going to obtain the other 3 is you fix, let's say that you take this cycle, you choose it so that it intersects the edges of the graph transversely, it doesn't go on the graph. And then you simply, you switch the orientation of all of these edges. And you do the same along this cycle, along one, along the other, along both, and you get the 3 other Castellan orientations, okay? You see what would happen if you, let's say that you want to, you do the same, but you change the orientation of all the edges that intersect a cycle that actually is trivial in homology. Then what would happen is that you're going to change, it's exactly the same as switching the orientation around the vertices inside the cycle. So what you would get then is an equivalent Castellan orientation. If you do this same trick along a cycle that is trivial in homology, then you get an equivalent Castellan orientation. If you do this trick along a cycle that is not trivial in homology, then you get non-equivalent Castellan orientations. Okay, this is just something for when you work out examples, that's important. I should have said this before. And now let me give you a corollary of the previous proposition. The corollary states that for any class alpha, we have the following equality. So if I sum over all equivalence classes of Castellan orientations, and I take the Arf invariant of Q omega m plus Q omega m of alpha, I always get 1. proof. So let me write this. Again, 1 over 2G sum over equivalence classes of Castellan orientations minus 1, this thing here. So actually, we just proved that this map here induces an equivariant bijection between Castellan orientations. So when I'm summing over all equivalence classes here, it is the same as summing over all quadratic forms, right? So here I can really write, so this is 1 over square root of the number of elements in H. Here H is H1 of the surface. Here I am summing really over all quadratic forms, minus 1 alpha invariant of Q plus Q of alpha. And that was a formula we had. That was, I think it was a fact B4 in this crash course on quadratic forms. Okay. Now we're ready for the proof. Good, so now we're going to put everything together, everything we did basically in this chapter. So we've been talking about these dimers and Pfaffians for, I think it's the 4th week now. And everything comes into place now in maybe a little bit more than one board. We can now prove the final result. So I'm going to show you how to compute in polynomial time, if you bound the genus, the partition function of the Dimer model on any graph. So let G nu be a finite weighted graph. So the first thing you have to do, of course, is you have to embed it in a surface. So embed well, maybe even before this. So first we want to assume that it admits the Dimer configuration. If it doesn't, there is no theory. So assume that it does admit a Dimer configuration, else, of course, the partition function is simply 0. Then what we can do is we know that we can find one in polynomial time. Okay, so then fix 1. Just going to fix a reference 1. This is possible in polynomial time by Edmond's algorithm. Okay, now we embed G in a surface, sigma, let's say of genus G. And we want to assume, as usual, that the complements are topological disk, such that is the union of topological disks. Now we fix a Castellan orientation omega on G embedded in sigma and let A omega be the corresponding skew agency matrix, right? Remember we had considered this be the corresponding, I would like to call it Castelline matrix. Remember we had defined this. It was in when we had proven the Castelline theorem. Whenever you have a weighted graph together with an orientation, then you can define a skew agency matrix. That's what I mean by this. As seen in, that was the very first paragraph, I think, of this part, we then have that the Pfaffian of A omega is equal to a sum over all perfect matchings on the graph of some sign epsilon. How did I write it? I think it was this way. Yes. You remember? And this was some sign, and the whole issue was this sign, right? Because if all these signs coincide, then we're done, we have the Poisson function. So now what we can do is, replacing omega by omega prime, which is equivalent to omega, one can assume that the sign associated to this reference perfect matching is equal to 1. If it's not, you replace omega by omega prime by just switching around a vertex, and it's going to change the sign of this. So you just, okay. So therefore, here I can multiply everything by this new sign. And now I continue to follow what we had done in this first paragraph. We had that this was equal to -1 power the sum over I n omega ci plus 1, where this was given by, oops, okay. Where we had, you look at the symmetric difference of these two perfect matchings and you get a disjoint union of CIs. Right, so these are these alternating cycles where you have dimers of M and dimers of M0 which alternate on them. So until here, until now I just basically repeated what we had seen 3 weeks ago. So now let's look at this number here. So all the information now is contained in this number here. So let's look at this. So now this is the miraculous line. So sum over I n omega ci plus 1. First, notice that on these cycles, so this is a typical cycle ci, we have that Lm0 of ci is always 0. How many dimers of M0 stick out to the left? None, because all of the dimers are on the curve itself. Okay? So note that here, Lm0 Ci is always 0. So here we'll just add this. Okay. So this is because but note that the CIs, they are simple closed curve, right? These are simple closed curve. They cannot self-intersect because, well, okay. So CIs, they are simple closed curves. So therefore, this is nothing but Q omega M0 of the class of this. And now remember, this quadratic form, it is not linear. But the defect of linearity is given by the intersection form. But here, these cycles, they don't intersect. They are disjoint. All the CIs are disjoint. So therefore, this, you can pass the sum inside. This is Q omega M0 of the sum of the CIs. And so here it's because the CIs are disjoint. But the sum of the classes of the CIs, this is simply the homology class of the difference. And so now if I put everything together, what do I get? I get that the Pfaffian of A omega is equal to a sum over M, and I have this sign, but this sign actually, and this is the whole point, this sign actually only depends on the homology class of the symmetric difference of M with this fixed M0. So now what I can do, I can put together, so I can sum up over the classes here, the homology classes. So I get -1 Q omega M0 of alpha. And then I group together all the dimers, all the dimer configurations that give the same homology class, this fixed homology class alpha. And okay, unfortunately, I just have to erase this, but you're going to use it in one line. So now let's look at the full partition function. The full partition function is simply the sum over all M of nu M. So what I can do here is sum up, so again, sum over all the classes, and then sum over all the M's that give this class nu M. And now I can use the corollary, so I'm going to introduce a number 1 here, which I'm going to expand as I had just erased with this huge sum. So I continue here. The corollary, what do we get? Sum over alpha, 1 over 2g, sum over equivalence classes of Cartesian orientation, -1 for Q omega M0 of alpha plus, so I had the RF invariant first, RF invariant Q omega M0 plus Q omega M0 of alpha So I rearrange these sums, so I have 1 over 2 power j, some classes of Castellan orientations, minus 1 RF invariant of this, and then I have sum over alpha, minus 1 q omega m0 of alpha, sum this. And you see that what we have here is precisely the Pfaffian omega. And so we're done. Theorem. With all the notations above, I'm not going to explain this again, we have that the Dimer partition function of a weighted graph is equal to 1 over 2 power g, sum over all equivalence classes of Castellan orientations on this graph embedded in the surface, so 4 power g different terms, some sign which is given by the RF invariant of the corresponding quadratic form, times the Pfaffian of A omega. And so what I would like you to understand from this computation is actually everything is happening here. So it's really, the whole point is, can we understand the sign that appears in the Pfaffian of a Castellan matrix? Or, yeah. And the whole point is, actually this sign only depends on the homology class of the perfect matching. It's symmetric difference with a fixed perfect matching. And not only this, but actually you can understand this sign as being some kind of quadratic form. It behaves as a quadratic form. So then, hence I have this Pfaffian here, which is equal to this thing here. And you can think that, okay, now I have a system with this number of unknowns. So the number of unknowns is the number of alpha here. The number of alpha is the number of elements here, that's 4 to the power g. And how many equations do I have? The number of equations is equal to the number of different Castellan orientations I have. That's also 4 to the power g. So it's a system that we can actually invert, and this is the meaning of this corollary I had. That's actually, I'm actually inverting this system. And so it's completely explicit, and you end up with this formula where everything is completely explicit and the sign has some geometrical meaning. It's the RF invariant of a related quadratic form. So I just finished with a couple of remarks. First remark, one thing I like about this formula is that the left-hand side here does not depend on the way the graph is embedded. This is something that is associated to the abstract graph, right? You don't need to embed your graph in anything to actually define the Dimer partition function. That's something on the abstract graph. And here, the right-hand side here really seems to depend. So actually, for example, you can take a graph and embed it in the plane or embed it in the torus. You'll have once a single Pfaffian, once 4 Pfaffians, but actually these two, they're going to be the same, because they're both equal to this thing to the left. So here, the left-hand side is independent, so only depends on the abstract graph. And so does the right-hand side, therefore. And I gave one example. I think it's exercise 2, homework 7, or let me just check. Yes, so I give a very simple example of a graph which you can naturally embed in the planar in the torus, and you try to make the computation. It's kind of funny to see that, well, okay, it gives the same thing. It gives the thing here. But you might have thought that this right-hand side, of course, depends on the way you embed your graph. It's not the case. And then, so the second remark, since I organized a little bit the class in this way, in this question of computability and complexity, this result shows that computing the Dimer partition function of a graph of bounded genus can be done in polynomial time. Okay, a genus of a graph is the minimal genus of a surface where you can embed it. So computing, so one can, so polynomial time computation of Z for graphs of bounded genus. Of course, if your genus is huge, then you have going to be it's going to be very long, because here you're actually computing, you're summing up over 4 power g Pfaffians. You're computing 4 to the power g Pfaffian, but it's bounded. Okay. Of course, this is not in contradiction with Valiant theorem, which was saying that in general it's not possible, because if you take just an arbitrary family of graph, then you might have your genus that just explodes. If the genus just grows, then your computation complexity here explodes, because you're going to have, you see, if your genus, let's say, augments in a linear way, then the number of computations of Pfaffians here augments in an exponential way, 4 to the power the genus. So, a good example to think about is to have in mind is the cubical lattice. So if you take cubical lattice and let's say 1 by 1, 1 by 1 by 1, 2 by 2 by 2, etc., and you grow it, obviously it's always a finite graph, so obviously you can always embed it in a surface of some genus, but actually the genus will grow exponentially in this case. So it means that you can, of course, each time apply this formula, but at each step you're going to have the number of terms here that appear that is going to explode. It's going to increase in a huge way. So it means that, of course, you're going to have your computation that will explode. But if you fix a surface, for example, if you fix yourself the torus, and then you consider, just graphs that are, let's say, finer and finer on the torus, then of course this formula is very useful. And one of the points of the next chapter is that actually on the torus, indeed, you can really do some really nice things. If you're on a higher genus surface, it's much more difficult. One reason being, if you're on a torus, there is a very natural way to make your graph finer and finer, right? So if you're a topologist, you think of covering spaces. You take coverings. If you're basically anything else, you just think normally and you say, okay, you just take your fundamental domain and you paste them together. And you can just paste them and it works. Okay. The advantage of being a topologist is that you can prove that it's the only surface on which you can do this, because actually covering spaces of the torus, the only surface that has covering spaces of itself is the torus, because the other characteristic is multiplicative by coverings. And so if you have a genus 2 surface, you cannot take coverings of a genus 2 surface by itself. So how can you make a graph finer and finer on the surface of genus 2? It's simply not obvious. There is no. So it's very difficult to use this to take continuous limits for in higher genus. But in genus 1, it's possible and it's been done, and this is basically going to be the subject of the next paragraph, of the next part. We will make this 15 minutes break now, so we start again at past, and I still have some things to say about this formula, some consequences, and then we're going to start the next part. Okay. Okay, so there was a very good question during the break. Somebody asked, but actually, is there a polynomial time algorithm to say if a graph embeds in a surface? So the answer is no, there is none. So meaning if you want to determining the genus that is the minimal genus of a surface in which a given graph embeds, this is an NP-complete problem. You cannot do it. But this is not a problem here, because here you don't need to embed it in a surface of minimal genus. You just imagine you have your graph, you start drawing it on the plane. Okay, you have it, so let's say you put all your vertices on the plane and you start drawing the edges. And whenever you're stuck, you just add a handle and you draw your edge along the handle. And maybe you're just a little bit stupid and you do too many handles, and at the end you find yourself with a graph where the faces have some genus, and you just cut the remaining one, the faces that are not disks, you just replace them by disks, and you are in the right situation where you can actually apply it. Of course, maybe it was you did it in a stupid way, and actually your graph was planar and you embedded in the surface of genus 15, but okay, it will work, okay. But it's true, but it is a relevant question. I mean, you cannot in polynomial time say if you are actually embedded in the right, in the best surface. One last remark here. As I already said, everything is contained just in this line here, which says the sign that is occurring in the Pfaffian of a Castellan matrix, it only depends on the homology of, okay. And there are many, many ways to give incomplete proofs of such a statement. And I gave one in exercise. So exercise 3 of this homework, I ask you to look at a paper, at an article where they give a proof in the case of the torus. And the exercise is try to find why it's incomplete. Okay. And yeah. Again, I am not claiming that there is no combinatorial proof of this statement. I'm not saying this. It is possible. It's just not a good idea. Okay, so I just want to give you maybe just a couple of examples first, and then talk about edge-edge correlations, because you can also apply this to compute edge-edge correlations. So examples. The first example, you all understood it already, I guess. If G is equal 0, then you have a single Castellan orientation up to equivalence, then the number of Castellan orientations is 2 to the power 2G is equal to 1, so you have a single one. And so you're summing over a single Castellan orientation, then you have this is equal to the Pfaffian of this. And here, remember, I cheated a teeny bit. So here you have to, remember, you have to take your representative so that the sign here is equal to 1. Because here, when you look at this, you think that's a little bit weird. You know, you have this sign here, which depends on M0. So we should have, so actually this thing here also depends on M0 in this way. It's just that I had chosen omega so that this sign is 1. So this is also why here you have a difference between this theorem here and Castellan theorem where you had absolute values. So this is because we had chosen omega so that this is equal to 1. And so this sign that we had is not appearing. So of course it's a new proof of Castellan theorem, but okay, that's not so exciting. And then G equal 1 is something that we will use. So we saw already that in the G equal 1 case, you have one quadratic form which is odd and the other ones are even. So there are 3 even quadratic forms. And one odd one. Hence, fixing a Castellan orientation omega, let's say omega equals omega 0, 0, and setting omega 1, 0, omega 0, 1, omega 1, 1 to be obtained from omega 0, 0 by the trick I had given in this remark. So you take your torus, you have your fixed Cassian orientation omega 0, 0, and then if you want omega 1, 0, you just invert the, you just change the orientation whenever you cross this thing here. If you want omega 0, 1, you change the orientation whenever you cross this thing, and if you want omega 1, 1, you change each time you encounter one of these. So by changing omega 0, 0 each time at each edge which crosses alpha, so respectively beta, respectively alpha union beta. That's the trick. Then we have z g nu is equal to 1/2 minus Pfaffian of A omega 0, 0 plus the three others. This is for the good choice of omega 0, 0, for the right choice. And this is a little bit, this just makes it a little bit annoying, but it's unfortunate. It's just the way it is. It is annoying to pick out which is the Castellan orientation, which will give you the negative sign. But once you have this one, then all the rest is completely fine. But okay, you have to compute things. Okay? And so I want to finish this part by talking a little bit about edge-edge correlations. So I'm not going to say much, but so this formula, so also allows to compute edge-edge correlations as follows. So the formula is not as nice as in the planar case. This time it's really not so nice, but it works. So let's say that we fix, so what were my notations? E1 like this, EK some edges. Okay, and then we set I to be equal to the ordered set. Remember we had these notations. And then what we try to compute is the probability that this family of edges appears in a perfect matching. And we had already seen that this can be given by the product of the weights over z times the partial derivative of the partial function with respect to these weights. Right, so this is simply, okay, we had seen this. And then now I can use this, the theorem. So what do I get? Mu E1, mu EK over Z, sum over equivalence classes of Castellan orientation, sine of the corresponding Arf invariant, so omega times 0. And then I have this partial derivative of a Pfaffian, which we know we have a formula for. And here, you remember, we have a formula for this, but only if A is invertible, only if the Pfaffian is non-zero. But anyway, here we're summing over the Pfaffian. So, well, Z is equal to sum of Pfaffian. So we can assume that we're only summing over omegas such that the Pfaffian is non-zero, right? So I'm summing over omega such that A omega is invertible. And then in this case, we have a formula. So that was, I think it was the property 5 and 6 of this discussion about the Pfaffian. So it gives, so there is a sign, -1 power k, mu E1, mu EK, sum over these Castellan orientations. And then here we have, so I just introduced a notation. Where Z omega is the Pfaffian of A omega. That is, we just saw that it was a sum. We have to see it as a twisted partition function, so, or a signed partition function. So we had seen what this was. So you just look at these formulas, and what you have is you have a Pfaffian of A omega which appears, and then you have this thing, so that's the inverse of this matrix, and you only look at the rows and columns that are indexed that correspond to these indices, right? We had seen this. Okay, so that's the theorem, and this is why I'm saying that it's not as beautiful as in the planar case. It's because in the planar case you have these two that actually cancel each other, and here it doesn't, so it's just a little bit more ugly. So we have that E1 EK is given by, sorry, I forgot the 1 over 2 to the power g. So it's mu E1 mu EK 2 power g sum over all these. Well, okay, I'm just repeating this line. It's not very useful. And again, it's a formula that is a little bit difficult to use if you're not in the planar or toric case. So, but I do want to write the form on the torus. So maybe just first a remark: if the graph is bipartite, if G is bipartite, then A omega has the form and one gets for EL being the vertex from the white vertex WL to the black vertex BL, basically we get the same formula but with Pfaffians replaced by determinant. So I will just write it. And it seems that when I did it in the planar case, I screw up the indices, but now I'll try to write them correctly. Okay. And so, okay, here it doesn't change. And here, so it's the determinant of k omega inverse. So how do I write this? Of bi wj for I and j 1 to k. I think in the planar case, apparently I had switched these two. It's not very important. Okay. And an example. So of course the g equals 0 case we already saw, but the g equal 1 case is new. What does it give? Well, it basically gives the following. So if we write, so writing 0, 0, 0, 1, 1, 0, 1, 1 for the 4 Castellani orientations, we have the following formula, and I want to write it because we're going to use it, actually. So it's E1 EK is so, yeah, sorry, now I just, here I want to write absolute values. Sorry, because there is this sign here. So I have this over 2. And then what do I have? I have a minus z 0, 0 over z. So that's the determinant of k 0, 0 inverse bi wj. And then plus the 3 others. And I'm not writing all the terms. So each time you, of course, have this, the corresponding determinant. And this is a formula that's going to be very useful for the study of the Dimer model on bipartite graphs on the torus, which is going to be the subject of this new part that I'm starting right now. Okay, that's the end of this. So it was what, part 1.2. We're still in part 1, which is the Dimer model. We had 1.1 perfect matchings on abstract graphs, 1.2 perfect matchings on surface graphs, and now 1.3. We're being more and more restrictive, but we're going to be able to say more and more about the model. Dimer models on, I'm going to say toric in parentheses because it's not going to be only about these, but mainly toric bipartite graphs. So right now we're going to restrict ourselves to bipartite graphs, and starting maybe next week, we're going to really look at bipartite graphs on the torus. And so this study has been so successful, this very particular case, that string theorists, for example, when they talk about a dimer, they mean a bipartite graph embedded on the torus, literally. So it's quite amazing the number of things that one can say. Well, basically, you can really solve the model in a very, very complete way. This case, and this is what I'm going to explain in this chapter. Okay, the first. And what is quite amazing also is that. So again, I had put the emphasis in this class on the amazing variety of tools that come into play. So here, the new tool that is going to come up is algebraic geometry. So it's not going to come up right away, but at some point you're going to see that algebraic geometry plays a key role in actually proving technical statements that allow you to solve the model. So first, 3.1, the height function. Okay. So it turns out that, maybe you saw this already, when you are on a bipartite graph, you can associate to a Dimer configuration a height function. But you need the graph to be bipartite and you need the graph to be embedded in a surface. The way I'm going to motivate this is through what is called gauge equivalence. That's the first little paragraph here in this part, and probably that's the only one I'm going to be able to finish today. So it's the following remark. So, okay, so we have a graph G, so let G be an abstract graph, so with weights, be an abstract weighted graph. Then remember we had defined a measure, so the Dimer model is defined by, so the measure of a perfect matching is equal to this, where just take the product of the weights of the edges in a perfect matching or a Dimer configuration. And now observe the following. So observe that the group what? So I want to consider the group of positive real-valued functions on the vertices of the graph. This acts on the set of weights on the graph, of the set 0, 80, and this is the set of edge weights on the graph, as follows. So let's say that we have S, which is an element of this group, and we have nu, an edge weight. Then you define S acting on nu of E. So you have to say what its value on E. So you just multiply the value. You have this value nu of E, and you multiply it by a value of S on both endpoints, if E has endpoints U and V. Okay, you can do this. But now observe that so I claim that this measure here is invariant under this action. So note that mu G nu is invariant under this action. Indeed, so let's just do the easy computation. So I want to understand what is, so this new edge weight system applied to one perfect matching M. So what is this? It's the product over all edges of M of, that is, S of U of S of V if E is equal to UV. Okay, but now you see that you can take out all the products of this S of U, S of V. And when you do this, since you have a perfect matching, meaning every vertex is adjacent to exactly one of these, each vertex of G will be counted once. So this is equal to a product over all vertices, S of V, times nu of M. And this is because M is a matching, perfect matching. So this is a constant, which does not depend on M. So it means that if you apply this action on nu, then you multiply the corresponding nu of M by an overall constant, which of course will also appear in the partition function, so this thing here will be unchanged. Okay. So this means, so maybe I can write, so mu G S applied to nu of M is equal to this constant here over this constant Z, so it's the same as mu G. The vocabulary for this is, the measure is gauge invariant. Invariant under gauge transformation. And one says also, okay, so vocabulary, so we say nu and S times nu are gauge equivalent. That's just terminology. And the measure mu is gauge invariant. So the bottom line is, if you want to understand the Dimer model on the graph, well, setting edge weights, actually, when you look at the edge weights, actually you have a lot of redundant parameters, right? So conclusion, there is a lot of redundant parameters in nu as far as the Dimer model is concerned. And so the natural question is it possible to reformulate the Dimer model using parameters that are not with no redundancy, so parameters that are themselves gauge invariant? Okay, question. Without meaning you're not going to set weights to the edges, but you're going to put some other family of weights that are fewer and that really have all the information. And the answer is, amazingly, it's possible, but with two. So yes, it's possible, but only if G is bipartite, first thing, and the graph is embedded in the surface, again. Only if G, well, that I know of, that people know of, okay? But if G is bipartite and embeds in a surface, and let's say is embedded. And this is this question of height function, so which you heard of maybe, that you assign, well, you will see. So maybe just the plan. So what we will do is first we're going to look at the planar case, which is easier. So do the planar case and then explain what changes in the surface case, in the general surface case. It's going to be using some more homology. And actually, this will also this will clarify something that I explained in the introduction. I didn't explain it, I just stated it a little bit. It was saying that actually, if you have a Dimer model on some regular graphs, then you can see this as a model of random surfaces, remember, of random stepped surfaces. So this will clarify also this view. This will also explain why the Dimer model is a model of random stepped surfaces. Can be seen as a model of stepped surfaces, as stated in the introduction. So basically next time, that's what we're going to do. So we're going to explain this formalism of height functions, how it works in general. And then I think that at that point, we're going to move straight to bipartite graphs on the torus. And then we're going to explain things there. This will probably take 2 to 3 full weeks. That's going to be the end of part 1 about the Dimer model. Then we're going to move to the Ising model. Okay, have a nice week.